strong versus weak acids and bases. In this case, we're looking at acids. Here I've outlined perchloric acid, chloric acid, chlorous acid, and hypochlorous acid. And they are in order of decreasing strength. Perchloric acid is the strongest, hypochlorous acid is the weakest. Now, you might ask, why is that the case? Why is perchloric acid the strongest? Well, in order to answer that question, we'll need to draw some Lewis structures, and we're also going to look at what happens upon dissociation. So, we don't actually need to look at the structure with the hydrogen in place. We actually should look at the structure without it to see if there's any differences between the perchlorate ion and the other ions. So, let's draw the Lewis structure for perchlorate. Chlorine is in the middle. And then we have oxygens surrounding it. And I'm going to skip directly to the answers here. And there's a negative charge on this ion. There's also a negative charge on the chlorate ion. So let's draw the Lewis structure of that very quickly here. There's also a negative charge here. Let's see here, ClO2 negative. And then ClO negative. All right, so each of these has a negative charge, and you'll notice that many of them have resonance structures. There's no reason why I couldn't put the single bond here and have the negative charge on this oxygen, but let's explore that a little bit, actually, because that's the reason why this is the best acid, or has the best acid. You'll notice that there's a negative charge on this oxygen. If we add up the number of electrons around it, there's 7. 1, 2, 3, 4, 5, 6, 7. So this has a formal charge of -1. There's a formal charge of 0 on the rest of the ions. Similarly, we have a formal charge of -1 here, and here, and there, and 0 on the other ions, or atoms. Now you'll notice that in this case, I can draw 3 more structures with the negative charge either being here, here, or there. The negative charge ends up being spread out over this entire 4 sets of oxygens here. And that helps it become stable, because anytime we can spread out the charge, it will be more stable. If we have a very focused charge, it will be less stable. So in this case, we're still able to draw some resonance structures with it. We could put the negative charge either here, here, or here. But there's one less place that we can put it. Whereas over here we have 4 places to put it. Now the charge is becoming a little bit more concentrated on these oxygens. Similar story here, only a little bit worse. Now we only have two positions to put the negative charge. And very bad here, the negative charge lives only on this atom. Well, according to the structure that's drawn. And there are no other resonance structures to help us out here. Well, how does this relate to the acid strength? Well, this ion is the most stable ion. It's easy to spread the negative charge around. That means that it will be easier for that hydrogen to leave because the charge is not localized at one position. Remember, we have an H plus and we have a negative charge ion. If that negative charge ion is focused in one position, like it is here, that hydrogen will be very attracted to that particular oxygen. Much less so over here because the charge is spread out. That stabilizes the charge and makes it easier for this ion to exist in a solution. And then these are in the middle. That story can play out also with nitric acid, for example. Nitric acid versus nitrous acid. Nitric acid is a strong acid, where nitrous acid is not. This is a weak acid. What's the difference between these two? In this case, I have more places for the negative charge to exist, and this one just has less. And so this one ends up being a strong acid, and this one does not. It's really about stabilizing the ion that exists in solution. That's also why when I talked about the fluoroantimonic acid, that it was a very strong acid, extremely strong. Well, one of the main reasons behind that is that the ion that's formed, that SbF6 negative, is very stable, has a lot of fluorines pulling on electrons so that that negative charge that's on that ion is very delocalized. It's delocalized over 6 fluorines. And fluorines have a very large electron affinity, or desire to have electronegativity, electron affinity, either way. And so that stabilizes that ion, and it allows the proton to be freer, because if the negative charge is not stabilized, then it's better for the positive charge to be nearby, because that way this one will not be exposed as negative. So more of this will be existing put together with the hydrogen than not. Whereas in these cases over here, that negative charge is much more stable, much more spread out. That makes it stronger.